I am KL Rajashree, Assistant Professor, Department of Mathematics. I am going to deal with the course name Numerical Methods, and the course code is U18Bsma401. So we are in this unit, we are going to deal with Unit 2 Interpolation. So in this unit, we are going to discuss the topics finite differences, relation between finite difference operator. Then we are going to deal with interpolation. In this interpolation, we are having two types, that is a Newton's forward difference formula and Newton's backward difference formula. Then we are going to do interpolation with unequal intervals. Then we are going to deal with Newton's divided difference formula. Then we have Lagrange's interpolation formula. In this, first we are going to deal with finite differences. So finite difference is a mathematical expression of the form f of x plus b minus f of x plus a. So next is the approximation of derivatives by finite differences plays a central role in finite difference methods for the numerical solution of differential equations, especially in the boundary value problems. Now next we are going to deal with the topic relation between finite difference operator. So finite difference deals with changes that takes place in the value of a function f of x due to finite changes in x. We are going to see only the finite changes. The finite difference operators include forward difference operator, which is denoted by delta, and backward difference operator, it is denoted by inverted delta. Then we have the shift operator, then central difference operator, and mean operators. So these are the few operators we'll be using in finite difference. In that, the important three operators are the forward difference operator delta, and the backward difference operator inverted delta, and the operator e. Here the operator e is defined by e of f of x is equal to f of x plus h, where h is the interval. So we can find the relation between the forward difference operator delta and e, and we can find the relation between the backward difference operator delta and capital E, and the operator E also. So your forward difference operator, it is equivalent to E minus 1. This can be derived. The derivation you can refer. Similarly, the backward difference operator inverted delta is equal to E minus 1 by E. And as already discussed, your E of f of x is equal to f of x plus h, where h is the interval which is given in the problem. So next is we are going to see Newton's forward interpolation. In the interpolation, we are going to discuss Newton's forward interpolation. So Newton's forward interpolation formula for equal intervals. So this formula, this interpolation formula is applicable only when the interval is of equal length. So let the function y equal to f of x takes the values. So the first value of y is y0, second value is y1, third value is y2, etc., etc. Last value is yn at the points x0. So when the function x0 we are giving the value, the value will become y0. If you are giving x1, the value will be y1, like that. So let the function y equal to f of x takes the values y0, y1, y2, etc., etc., yn at the points x0, x1, etc., to xn, where xi is equal to x0 plus I into h. And then the Newton's forward interpolation polynomial is given by y of x is equal to Pn of x0 plus uh is equal to, we are actually introducing an variable u, that u is given by x minus x0 by h. So y of x is equal to Pn into x0 plus is equal to y0 plus u power 1 into delta y0 by 1 factorial plus u square into delta square into y0 by 2 factorial plus u power n into delta power y0 by n factorial. So as we have discussed, your u is given by x minus x0 by h. So Newton's forward interpolation formula is y is equal to y naught plus u into delta y naught plus u into u minus 1 by 2 factorial into delta square y naught plus u into u minus 1 into u minus 2 by 3 factorial into delta cube y naught plus etc. etc. It is an infinite series. So where your u is given by u is equal to x minus x naught by h. So this formula is mainly used for interpolating the values of y near the beginning of a set of tabular values. So for the beginning values only, we'll be using forward interpolation formula. So depending upon the problem given, you have to check whether you have to use forward interpolation formula or backward interpolation formula. So you have to compare the value for which we are finding the value, whether we have to check whether it is in the beginning of the set of tabular values or at the end of the set of tabular values. If it is in the beginning of the set of tabular values, you have to use Newton's forward interpolation formula. So we are going to discuss a problem based on Newton's forward interpolation. So using Newton's forward interpolation, you have to find the polynomial f of x satisfying the following data. Hence evaluate y at x is equal to 5. So some x values are given, some y values are given. So the x values given are 4, 6, 8 and 10. The corresponding y values are 1, 3, 8 and 10. So we will take your y as f of x. So we are going to form a table. So if the table, the columns are x, f of x, del into f of x, del square f of x, del cube f of x, the derivatives. Then column wise, we are writing the values of x given. So 4, 6, 8 and 10. Now we are writing the corresponding values 1, 3, 8 and 10. So now we are going to find the first differential operator, that is del f of x. So from the second value you have to subtract the first value. So your 3 minus 1 will give you 2. So come to the third data, that is 8. From 8 you have to take away 3, so you will get 5. So from 10 you have to take away 8, so that will give you 2. So you have got your del f of x. So if you are making mistake in the del f of x, that will affect del square f of x. So you should be very careful in calculating the values. So next we are going to take the second order differential operator del square fx. So for that we have to subtract 5 minus 2, that will give you 3. Next case 2 minus 5. So 2 minus 5 will give you minus 3. So you have got the column del square f of x, that is the second order derivative. Now we have to go to the third order derivative, that is minus 3 minus 3, that will give you minus 6. So Newton's forward interpolation formula, there are only 4 data given. So hence the polynomial will be of degree 3. So y of x is equal to Pn of x naught plus uh. That is equal to y naught plus u power 1 into del y naught by 1 factorial plus u square into delta square into y naught by 2 factorial, etc. etc. un del power n y naught by n factorial, where your u is given by x minus x naught by h. So what is the initial value of the data, that is x naught is equal to 4, and the interval here is for 0, 1, 2, 3, 4, like that it is given. So your h is 2. So your y of x will be minus x cube plus 21x square minus 126x plus 240 by 8. So if you simplify that, you are getting a polynomial and you are asked to find the value. So y of 5. So give x is equal to 5. So you will get the value minus 5 cube plus 21 into 5 square minus 126 into 5 plus 240 by 8. So if you are using the calculator, you will be getting the value of y of 5 as 1.25. So Newton's forward interpolation formula, you are given u0 is equal to 1, u1 is equal to 11, u2 is equal to 21, u3 is equal to 28 and u power 4 is equal to 29. You are asked to find out del power 4 of u0. So you are just forming the forward interpolation table. So as discussed in the previous slide, we are writing the value of x in the first column, ux, that is y is equal to ux in the second column. Then third one, first derivative you are writing as 1 u of x, then 2 u of x, 3 u of x, and 4 u of x. So 11 minus 1 will give you 10, 21 minus 11 will give you 10, 28 minus 21 will give you 7, and 29 minus 28 will give you 1. Now, in the second column, 10 minus 10 will give you 0. 7 minus 10 will give you minus 3. 1 minus 7 will give you minus 6. So your third column will be 0, minus 3, minus 6. So minus 3 minus 0 will give you minus 3. And your minus 6 minus of minus 3. So that will become plus 3. So minus 6 plus 3 will become minus 3. So minus 3 minus of minus 3, that will become 0. Hence your fourth order, that is del power 4 of u0 will be 0. Next is, based on this, you are given two problems. Obtain the interpolation quadratic polynomial for the given data by using Newton's forward difference formula. So you are given the data, x values are 0, 2, 4, and 6. Y values are minus 3, 5, 21, and 45. Now next, using Newton's forward interpolation, find the polynomial f of x satisfying the following data. You are asked to find the value at y equal to x is equal to so. So previous problem, you are not asked to evaluate the value of y. You can just form a quadratic polynomial. So here you are after finding the value of the polynomial, you have to evaluate y at x is equal to 2. So like the previous problem, if you have to give the value of x as 2, you will get the answer. Next is Newton's backward interpolation. So Newton's backward interpolation formula for equal intervals. So we are taking same like the forward interpolation. Let the function y equal to f of x takes the values y0, y1, etc., etc., yn at the points x0, x1, etc., xn, where xi is equal to x0 plus ih. Then the Newton's backward interpolation polynomial is given by this series. Here we are going to introduce a variable small v. That small v is given by x minus xn by h. So your y of x is equal to Pn of xn plus vh is equal to yn plus v power 1 into inverted delta yn by 1 factorial plus v square into inverted delta square yn by 2 factorial, etc., etc., vn inverted delta power n yn by n factorial, where your v is x minus xn by h. Now, Newton's backward interpolation formula is given by Newton's backward interpolation formula is y is equal to yn plus u into inverted del yn plus u into u plus 1 by 2 factorial into inverted del square yn plus u into u plus 1 into u plus 2 by 3 factorial into inverted del cube yn, etc., etc. So it is an infinite series where your u is given by x minus xn by h. So this formula is used mainly for interpolating the values of y near the end of a set of tabular values. So forward interpolation, the values will be at the beginning of the tabular values, whereas the backward interpolation, we are mainly using it for finding the values of y near the end of a set of tabular values. So we are going to use Newton's backward interpolation formula. Based on that, we are going to discuss a problem. So using Newton's backward interpolation, find the polynomial of degree 3 for the following data. So your x values are given like minus 0.75, and you are given a very lengthy value, that is minus of 0.0718125. Next, the x value is minus 0.5 and minus 0.0244750 and minus 0.25, 0.033493750. And next is 1.10100. So we are, as usual, we are writing the x values at the first column, f of x values or the y values in the second column. Next, we are find the first derivative, that is del f of x. Next column, we will find the second order derivative, del square f of x. Then we will be finding the third order derivative, del cube f of x. So we'll be writing, stating the values of x, minus 0.75, minus 0.5, minus 2.5, minus 0.25 and 0. And the y values are minus 0.07181250, then minus 0.024750, then 0.334933750, then 1.10100. So we are going to find the first derivative, that is del f of x. So minus 0.024750 minus of minus 0.07181250. So if you find the difference, you are getting 0.0470625. Next case, 0.334933750 minus of minus 0.024750. So that will become plus. So if you do the calculation using calculator, you will be getting the value 0.3596875. Next value is from 1.10100 minus 0.0334933750. So if you use the calculator, you will be getting the value 0.7660625. So from that, we are going to the second derivative. So for that, we have to calculate this way: 0.3596875 minus 0.0470625. So if you are using the calculator and if you are computing the value, you'll be getting 0.312625. Now from the first derivative, that is 0.7660625 minus 0.3596875. If you use the calculator and if you calculate the value, you will be getting the answer 0.400375. Now we are coming to the third order derivative, that is del cube f of x. So for that, you have to take this way: 0.400375 minus 0.312625 will give you 0.09375. So the tabular column is over. Now you are going to use the Newton's backward interpolation formula. So your y is equal to yn plus u into inverted delta yn plus u into u plus 1 by 2 factorial into inverted del square yn plus u into u plus 1 into u plus 2 by 3 factorial into del cube inverted del cube yn, etc., etc. So your y of x is equal to x cube plus 4.0001 into x square plus 4.002 into x plus 1.101. So if you are calculating the value of y at the point minus 1 by 3. So you have to give x is equal to minus 1 by 3. So you'll be getting y of x is equal to minus 1 by 3 the whole cube plus 4.001 into minus 1 by 3 the whole square plus 4.002 into minus 1.1 by 3 plus 1.101. So if we simplify this value using our calculator, you are getting a y of minus 1 by 3 as 0.174518518. So based on this, we are given two more problems to work out. So that is using Newton's forward interpolation formula, find the polynomial f of x satisfying the following data, hence find f of 12. So your x values are given as 0, 5, 10 and 15. Your f of x is 14, 374, 1444, 3584. So here you are asked to find the value of f of 12. So it comes in the beginning of the data. So we are using forward interpolation. Next question is, from the following table, find the value of tan 49 degrees 15 minutes by Newton's forward interpolation formula. So here too, your data is given are 45, 46, 47, 48, 49 and 50. So tan x degrees will be 1, then 1.03553, 1.07237, 1.11067, then 1.15037 and 1.19175. So using this you have to calculate the value. So next is divided differences. So divided differences is, let the function, we are going to define what is divided differences. Let the function y is equal to f of x takes the values f of x naught, f of x1, f of xn, etc., etc., corresponding to the values x naught, x1, etc., etc., xn, where the argument x, where the of the argument x, where x1 minus x0, comma x2 minus x1, etc., etc., xn minus xn minus 1 need not be necessarily equal, because that is the successive differences, they may not be equal. So the first divided difference of f of x for the argument x0, x1 is defined as f of x0 comma x1 is equal to f of x1 minus f of x0 divided by x1 minus x0. So next we are going to see the properties of divided differences. The divided differences are symmetrical in all their arguments. That is, the value of any difference is independent of the order of the arguments. So the divided differences are symmetrical in all their arguments. That is, the value of any difference is independent of the order of the argument. So the value of any difference, it does not depend on the order of the argument. That is what they are saying, the property. Next is the divided difference of the sum or difference of two functions is equal to the sum or difference of the corresponding separate divided differences. So first we are taking the sum of two functions, sum or difference of two functions. We can take the sum of two functions, or we can take the difference of two functions, that is equal to the sum or difference of the corresponding separate divided differences. So the sum of the two functions will be equal to the sum of the separate divided differences. Similarly, difference of two functions will be equal to the difference of the corresponding separate divided differences. The next property is the divided difference of the product of a constant and a function is equal to the product of the constants and the divided difference of the function. So first we are taking the divided difference of the product of a constant and a function. Next, that will be equal to the product of the constant and the divided difference of the function. Next is the nth divided difference of a polynomial of nth degree will be constant. So if you take the nth divided difference, the polynomial of nth degree will be a constant. Suppose if you are taking the third divided difference of a third degree polynomial, it will be a constant. If you take the fifth divided difference of a 5 degree polynomial, that will be a constant. So in general, we can tell like this, that is the nth divided difference of a polynomial of nth degree or constant. Next is Lagrangian interpolation. So Lagrangian interpolation, the Lagrangian polynomial method is a very straightforward approach. The method perhaps is the simplest way to exhibit the existence of a polynomial for interpolation with unevenly spaced data. That is, data where the x values are not equispaced often occur as the result of experimental observations or when historical data are examined. So the Lagrangian interpolation formula is given by f of x is equal to x minus x1 into x minus x2 into x minus x3, etc., etc., x minus xn. Your denominator will be x0 minus x1 into x0 minus x2, x0 minus x3, etc., etc., x0 minus xn into y0 plus x minus x naught into x minus x2 into x minus x3, etc., etc., x minus xn divided by x1 minus x naught, x1 minus x2, x1 minus x3, etc., etc., x1 minus xn into y1 plus x minus x naught, x minus x1, x minus x3, etc., etc., x minus xn divided by x2 minus x naught into x2 minus x1, x2 minus x3 into x2 minus xn into y2, etc., etc., x minus x naught into x minus x1 into x minus x2, etc., etc., x minus xn minus 1 divided by xn minus x naught, xn minus x1, xn minus x2, etc., etc., xn minus xn minus 1 into yn. So whatever you are getting the the subscript of y, that is y naught, y1, the denominator will be having the same thing. Here if it is y naught, here it starts with x naught. Here it is y1, here it starts with x1. If it is y2, here it starts with x2. Here if it is yn, it starts with xn. So Lagrangian, what are the advantage of Lagrange's formula over Newton's formula? So Newton's formula can be used only when the values of the independent variable x are equally spaced. But Lagrangian interpolation formula can be used whether the values of the independent variable x are equally spaced or not. So Lagrange's formula can be used for inverse interpolation also, where Newton's formula cannot be used. This is the advantage. So what is the disadvantage in practice applying in Lagrange's interpolation formula? It requires close attention to sign, and there is always a chance of committing some error due to the number of positive and negative signs in the numerator and denominator. So this is the disadvantage. So what is the difference between Newton's divided difference formula and Lagrange's formula? Lagrange's formula is merely a variant of Newton divided difference formula. Next is, what is the inverse interpolation? It is the process of finding the values of x corresponding to a value of y not present in the table. So that is the inverse interpolation. So what is the Lagrange's formula to find y if three sets of values x naught, y naught, x1, y1, x2, y2 are given? So y is equal to f of x is equal to x minus x1 into x minus x2 divided by x naught minus x1 into x naught minus x2 into y naught plus x minus x naught into x minus x2 divided by x1 minus x naught into x1 minus x2 into y1 plus x minus x naught into x minus x1 divided by x2 minus x naught into x2 minus x1 into y2. So write the Lagrange's formula for inverse interpolation. So it is x is equal to f of y is equal to y minus y naught into y minus y1 into y minus y2, etc., etc., y minus yn divided by x2 minus y2 minus y naught, y2 minus y1, y2 minus y3, etc., etc., y2 minus yn plus y minus y naught into y minus y1 into y minus y2, etc., etc., y minus yn minus 1 divided by yn minus y naught, yn minus y1, yn minus y2, yn minus y3, etc., etc., yn minus 1. So using this, find the quadratic polynomial that fits y of x is equal to x power 4 at x is equal to 0, 1, 2. So the following data is 0, 1, 2, y is equal to x power 4. So your answer will be 0, 1 and 16. 2 power 4 will be 16. So by Lagrange's formula, y is equal to f of x is x minus 1 into x minus 2 by 0 minus 1 into 0 minus 2 into 0 plus x minus 0 into x minus 2 by 1 minus 0 into 1 minus 2 into 1 plus x minus 0 into x minus 1 by 2 minus 0 into 2 minus 1 into 16. So if you simplify, you will get y is equal to minus x into x minus 2 plus 8x into x minus 1. Further, if you simplify, you will get a quadratic polynomial, that is y of x is equal to 7x square minus 6x. So Lagrangian interpolation. Find the polynomial f of x by using Lagrange's formula and hence find f of 3 for the data. The values of x are 0, 1, 2 and 5 and value of f of x are 2, 3, 12 and 147. Thank you.